So hi everyone, I'm Sean Pham, the CEO of BioTuring. Welcome to BioTuring Single Cell Webinar. In BioTuring Single Cell Webinars, we invite scientists with important discoveries using single cell technologies, or scientists who invented important algorithms for single cell data analysis. For the last 3 years, unarguably, Umap is the most commonly used algorithm for visualizing high-dimensional single-cell data. Today, it's my great pleasure introducing John Healy, the author of Umap. John is a mathematician and a computer scientist at the Third Institute for Mathematics and Computing. Besides Umap, John is also the author of HDB Scan, a density-based clustering algorithm. So today, John will give us a practical guide to Umap. The talk durations will be expected to be 30 minutes and followed by question and answer. All right, welcome, John.
Thank you very much. Let's see if I can take over the screen sharing. All right. Can you see my slides, Son?
Yes,
Okay.
I can see your slides.
You can see all your slides, yes.
Hello, everyone. Again, thank you for the kind introduction. It's very nice of you to invite me to give a talk here. I'm excited to be talking to a lot of non-mathematicians and people who make use of Umap to do real things in the real world. That's quite exciting from my point of view as well. As Son said, I'm John Healy. I'm a researcher at Tutt Institute for Mathematics and Computing. We're a small government-funded research institute in Ottawa, Canada. I'm here to talk to you about a dimensional reduction algorithm we developed a few years back called Umap, or Uniform Manifold Approximation and Projection. Before we get started, I'd like to emphasize this is all joint work with a colleague of mine, Leland McInnes, who's been taking the lead on our Umap project. Like any good open source project, the project has expanded well beyond our initial work and has now been worked on by a number of other people from a great variety of backgrounds from all around the world. And we're super excited that that's been the case. I'm going to give a short whirlwind tour through some of the considerations you should take into account when performing dimensional reduction in general and Umap in specific. While doing that, I'm also going to point you to a few of the more esoteric features that we've added to our Umap library over the past few years, which might help you in your day-to-day dimensional reduction tasks. Since this is a 30-minute-ish talk, I'm going to not going to go into much depth on any given topic, but I'll try to provide links where I can so you can dive more deeply into whatever piques your curiosity. All right, first off, as Son mentioned, I have a confession to make. I am not a biologist. I don't even play one on TV. I'm a mathematician. My background is statistics, machine learning, and data science. As such, I'm going to be giving a very general talk and not tailored to biology in any particular way. I'm happy to chat more about specifics and your data and how this is applied in your lives after the talk. That sounds super exciting. I'd love to learn from all of you. All right. Machine learning is largely divided into supervised and unsupervised learning. In supervised learning, we have labels, and we develop algorithms which are good at reproducing those labels. In unsupervised learning, you apply known algorithms to your data and reveal structures contained therein. All right. I tend to take the viewpoint that unsupervised learning consists of a set of lenses. Different algorithms or lenses provide different views or perspectives on your data. As such, unsupervised learning can provide wonderful insights into any new data set. I would argue that it's the first thing you should always do when confronted with a new problem. It's to go and look at your data and then do science. In other words, unsupervised learning can reveal interesting structures contained in your data, as well as potential errors in your coding or experimental design. And that's really great and really fun to play with. But at the end of the day, those insights need to act as driving forces to help scientists like you develop hypotheses, which can then be tested via rigorous scientific methodologies. I'm sure this is a topic that everyone in this virtual room is more qualified to talk about than I am, that this is a good step in a process. It's not the end of a process. All right. It's enough philosophy as unsupervised learning. Let's delve into dimension reduction. For our purposes, I'm going to define dimension reduction as finding a low dimensional representation of our data, which is useful for some task. Leland gave a really nice, fun overview of dimension reduction techniques back in 2018. I had a variety of these techniques, which are in common use. I'd recommend it to anyone with a broader interest in dimension reduction. Easy to Google for this if they would like. All right, now let's talk about dimension reduction as a lens. First off, a thing that is characteristic of all our lenses is that different algorithms or lenses perform differently on different goodness measures. Maybe you care about reconstruction error, maybe you care about local structure. Perhaps you've got a downstream task for which your dimension reduction is just a pre-processing step. Either way, there's no one algorithm to rule them all. There's no single best goodness measure for all problems. The key is to understand your particular use case and find a goodness measure that's right for that task. As such, I feel you should always be a bit skeptical anytime someone comes along and tries to tell you that they've found the best goodness measure and that their algorithm is better than all other algorithms because they score better on that measure. Maybe that measure is great. Maybe it isn't. Either way, it very likely isn't the right measure for all use cases. All right, I'm going to start us off by flicking through a handful of common lenses and talking about how they behave with respect to an interesting feature that I think is common to a lot of data, variable density. So here is a very simple pair of three-dimensional point clouds sampled from a pair of Gaussian distributions. You can tell that the variance of the blue point cloud, which looks like a tiny dot in the middle of your screen, is significantly smaller than the variance of the red point clouds. Okay, I think examining how different algorithms represent this data in 2 dimensions will end up being enlightening. Umap will assume that there exists a manifold on which the data is uniformly distributed and then try and find it. And here's what that looks like. That uniform manifold assumption caused us to flatten out the variations in density that we saw in our data. But it did sacrifice some information to do that. From this plot, you can't tell that they had hugely variable density in your original ambient space. Principal component analysis, or PCA, on the other hand, will try and find a 2-dimensional plane of best fit through this data and then project down onto it. So while Umap lets us see all of the structure contained within your data at one glance, the advantage of PCA in this sort of a situation is that both tools are useful for revealing different things about your data, and both have their place in your toolbox. Multi-dimensional scaling is another quite popular technique. It emphasizes the preservation of distances. This puts it very much in the same general camp as PCA, as can be seen from these sorts of results. That said, MDS won't always generate the same embeddings as PCA, but this very simple case shows that they're lining up almost perfectly. Spectral embedding is one of the more famous members of a class of algorithms called manifold learning. In general, this family of techniques tend to emphasize local structure at the expense of global structure. Once again, you can see that in this flattening out of the density of that data set we just looked at. This is a pretty common occurrence across the class of manifold learning algorithms in general. All right,
John,
which of these techniques is telling you the truth about your data? Yeah, what's up?
It seems to me that the signal from your side is interrupted, a little bit.
Oh, well, that is very disappointing. Let me see what I can do. Do you want me to try to reconnect and connect again? Or
come a little bit closer to the Wi-Fi?
I can pick. Let me check my Wi-Fi. Yeah, that sucks. One moment. So I am super close to the Wi-Fi now. I will move the router a tiny bit closer to my laptop, and hopefully that will do something good. One moment.
Okay, okay, this sounds good now.
I see in the chat the connection is much better now. Is that, or is it just an intermittent?
That's right. We can hear you much better.
Okay, well, fingers crossed that that will be that will stay working. I can't see the chat very easily while looking at slides, so Son, the right thing to do is interrupt me with
all right.
If something like that comes up.
I'm here.
Perfect. All right. All right. All right. So which of these things tell the truth about your data? The short answer is all of them, or maybe none of them. They all tell you some truth about your data, but none of them tell you all the truth. All right. Which is best? Again, it depends. That's akin to asking a carpenter which tool is best. The answer will inevitably be the tool that is most suited to your task at hand. In short, all lenses distort your view. Some of those distortions are useful. One consistent thing to keep in mind across all of these lenses is that they either implicitly or explicitly depend on a notion of distance or similarity. I like to think of an embedding as a numerical representation of your data along with the distance measure. The two components are sort of the most important aspects of dimension reduction. Traditionally, you need to either provide a meaningful notion of distance or have labels so you can learn a useful notion of distance. I'm not going to talk about distance measure, which should come up anytime you're thinking about doing unsupervised learning. All right, let's go into more depth on the Umap lens itself. A nice way to characterize Umap is as a useful tool for embedding complex structural relationships into a more comprehensible representation. It's one of those manifold learning techniques that I mentioned earlier. The basic idea is that the intrinsic dimensionality of the data is lower than the ambient dimensionality we're presented with. As such, we don't really trust the distances between our points, which are far away from each other. All right, to find that intrinsic dimensionality, we're going to pick a distance measure, draw an edge for each point to its k-nearest neighbors. We'll reweight that graph. We use that as a proxy for our manifold, or by manifold being the surface your data lives on. Then we're going to find a low dimensional representation of our data, which could have induced the same graph. The details and justifications will vary from algorithm to algorithm. In general, these are the basic steps of sort of any manifold learning technique, and Umap in particular. All right, let's go through a few practical things to keep in mind regarding each of those steps. Choose your distance measure. This one's on you, and ideally incorporate some of the knowledge you have about your data. It's worth thinking about because it can have an impact on your results. Build your k-nearest neighbor graph. This emphasizes the local structure over global structure contained in your data. The smaller the k, the more locally you're focused. This choice purposefully sacrifices fitting your long distances as they are no longer present in your representation. We got to weight that neighbor graph. This is our local relative notion of distance. This will distort your original ambient space. In Umap, you're saying that local distances are sort of dependent on local density. The notion of far means something very different if you're walking around downtown Ottawa or your city of choice versus you're standing by the side of the road amidst cornfields and the prairies. Far is a much broader notion in the second case. Now, you're going to symmetrize that neighborhood graph. And here's the key. Neighbor graphs are non-symmetric. Everyone might feel that Ryan Reynolds is their best friend, but that doesn't make them Ryan Reynolds' best friend. So you have a non-symmetric relationship in any of these nearest neighbor graphs based on your local neighborhood. Embedding our graph into a metric space requires some notion of symmetrization. You need to deal with that, the ambiguity of those different relationships. And this by itself is going to distort your nearest neighbor structure. And so embedding this non-symmetric graph into a metric space will inherently distort that structure. It's something you need to keep in mind anytime you're doing one of these techniques. Finally, we need to embed the graph into a metric space. There's lots of ways we could do this, but Umap uses a stochastic algorithm to find a low-dimensional embedding that would have built the same graph. The disadvantage of this stochastic optimization is going to be a lack of stability, which we'll talk about a little bit more later on. All right, I'm only giving a 35-minute talk, so I'm not going to go into any theoretical details or mathematical justifications. I've included some links to our original paper and a few excellent talks that Leland has given over the past few years, if you're interested in looking into more details on those. If we're getting a better intuitive understanding of our parameter space, I'll recommend this great interactive article by Andy Coenen and Adam Pierce from Google. You can play around with all the parameters, and it really does a good job of explaining and providing a good intuition on how they work. Speaking of parameters, we have a lot of them in Umap. That's essential foray into Umap into a handful of the most useful parameters. There's lots of documentation on getting you started over at Read the Docs, but the short version is n neighbors is your basic resolution parameter. N components is the dimension you'd like to embed into. For visualization, that's usually 2, but you could easily embed into higher dimensions if you'd like. Metric is the metric in your original space. That is the distance function I alluded to earlier. This can be bypassed if you set it to equal the string pre-computed, and then you build your own square distance matrix. That can be quite expensive, and that can be quite memory consuming, but it's an option if you have more complicated distance functions than any of the ones that we're providing. Random state lets you get consistent results from run to run, and unique is a Boolean that deals with excessive numbers of exact duplicates that appear in your data set. I'll talk about more on that one a little bit later on in the talk. All right, now that we can build a model, well, the next thing I tend to suggest to people is to look at your data. One way to do that is to grab the coordinates of the embedding and throw them over to matplotlib or Seaborn, Bokeh, Plotly, TensorBoard, your visualizer of choice. They're in the .embedding underscore property of your model. Grab them, have a look. That's a fun hack. You can, in fact, overwrite them with the new coordinates from another transformation if you're feeling keen. Warning, it's a bit of a hack, but I tend to do this when I'm trying to align two embeddings that are to make them more visually similar. That'll match them up. I'll overwrite the embedding with the Prusty's aligned version, and I'll continue on. Why would I do that directly in the Umap instead of in some other piece of the software? Good question. I would do it so that I can make use of our very lazy plotting functions. So Umap isn't a plotting library, but we've wrapped a few of the common visualization steps up to make our lives and those of our users a bit easier. We've got a couple of basic static plot functions, which we'll call either matplotlib or datashader, depending on how much data you've got. We've also got a quick and dirty interactive visualizer with a simple hover tool, which is sort of a mouse over tool, which is probably the most natural way to explore your two-dimensional embeddings. The hover tool breaks for really large amounts of data, but we've added a subsampling option ahead of your points and just visualize those with some added mouse over hover data information. Either way, these functions can help you quickly construct nice visualizations like these ones we saw earlier. Now, when you were looking at these ones earlier, you might have been uncomfortable when I showed that Umap was normalizing away the relative densities of those Gaussian point clouds. Again, I'll claim that discomfort should depend on your particular use case, but you might easily ask, can I reveal that local structure without completely losing sight of the differences in density? The answer is yes. That's what you like to do. Then you can set.
There's a small interrupt.
What do we got?
Probably we can. John can turn off your camera to save.
Sure, I could totally do that. Let's see. Zoom. Minimize this. Stop. All right. Hopefully that improves things.
Yeah, theoretically it should.
Theoretically is correct. All right. Let's try this again. Get my screen back. All right. Fair enough. All right. So if the answer is yes, then you can set your dense map parameter here to be true, and you're off to the races. So dense map is a variation on UMAP, which works to preserve some of the local density of your original ambient space. This was originally a paper by Narayan, Berger, and Cho in Nature Biotechnology. You can give that a read, or if you want looking for something a little bit lighter, then you can look at the Read the Docs page. All right. Next on our whirlwind guide through using UMAP, there's an interesting notion of consistency. So there's no canonical UMAP embedding of a given data set. You may recall that the final step of UMAP is a stochastic optimization, which is a fancy way of saying we throw down our points and then move them around until we find a good set of coordinates to optimize our objective function. What that means in practice is that the structure of our plots will look fairly similar from run to run, because they're based off the same graph and they were initialized with the same coordinates. But fairly similar isn't the same. Perhaps from these plots, it's a little bit hard to see that they don't exactly match, but if we overlay them on top of each other, you see that there are significant differences. Here, the blue points are from the left embedding, the red points from the right embedding. We see they match in general shape, but they differ in the details. All right. The easiest way to get some consistency for sharing your work or publishing system results in a paper is simply setting the random state. Here we set the random state to 5, and we get consistent results from side to side. Very straightforward, not hugely satisfying, though. It doesn't answer the question of consistency when you have introduced new points. The short answer to the problem of new points is to apply a dot transform function to all of your data. That you take a little bit of new points or a lot of new points, you put your old points through, you apply dot transform, you embed them all into the same joint space. The longer story is that mostly works well for very small amounts of novel data. And that's because the transform function in UMAP isn't particularly quick. If you expect to map large quantities of data into a learned UMAP space, then you probably want to look at parametric UMAP, which depends on a TensorFlow architecture for constructing a functional neural network mapping from your original space into your low-dimensional UMAP embedding. Adding new points to an existing embedding with a learned parametric mapping is very, very fast. If you look over here, you can note that this is a log scale. The dark blue bar represents parametric UMAP running on a GPU. And for comparison, the dark purple bar is principal component analysis, which is one of the fastest dimension reduction algorithms we've got. And so you see comparable results between GPU parametric UMAP and principal component analysis for transforming data. This is not for learning the initial embedding. This is for transforming new points into that joint space. For contrast, you can see over here, this is parametric UMAP running on a CPU, and the dark blue bar on the far left is our normal dot transform function from UMAP. And so significant speed ups if you need to be transforming large amounts of data. The code is pretty straightforward. Again, this all fits with the sklearn architecture, which is great, an API. You can find more details in this very nice paper by Sainberg, McKennis, and Gentner, or again, on the Read the Docs page. All right. Now, what if your data sets come from different but overlapping distributions? Trying to apply a dot transform to data, which your training data was not representative of, can be a very, very dangerous game. Maybe your underlying data is non-stationary. Maybe you have a nasty sampling bias in your original data acquisition. Either way, what can we do? All right, I'm going to simulate that happening by taking 2 copies of our fashion MNIST data set and removing a few clothing classes from each. Each point here is an embedding of a clothing image. They're colored by the label associated with that piece of clothing. This results in a challenging spot the difference puzzle, made harder by the fact that due to the stochastic nature of the algorithm we mentioned before, we have flipped a few of our structures around. If you're watching a recorded version of this talk, feel free to pause it and play Spot the Difference. But for the rest of us, we're on the clock, so I'll give you the answers right now. 5 and 7, the clothing classes associated with 5 and 7 are missing from the picture on the left, and the clothing classes labeled 3 and 4 are missing from the picture on the right. All right. We can deal with this problem using a aligned UMAP, which is going to anchor the set of points that these embeddings have in common to each other and apply a regularization penalty for moving them away from their coordinates, their joint coordinates. These are anchors. These anchors are relationships. They're provided by dictionaries that give you links between the common points in both data sets. In this case, these dictionaries specify the mapping between the data samples. They're common in our leftmost and rightmost data set. And this is the result. We see the structures in common across both sets have lined up very well, and the missing data from each case is integrated nicely into our embedding. Of course, aligned UMAP has a variety of other uses. Most of them revolve around some variation of adding time to our embedding. It's reasonably inexpensive if you're just lining up pairs of embeddings, but can get very, very expensive if you want to align a large sets of embeddings all at once in a non-iterative pairwise fashion. You can hand it 10 embeddings and say, line up all of these, and that gets pricey. All right, on the subject of dealing with multiple embeddings, we're sometimes confronted with the question of what the right way might be to fold together embeddings of the same data from different spaces. One way you might do that is to just reduce the spaces independently and glue together the resulting spaces by looking at sort of the joint cross product space. What that generally looks like is you reduce one feature space to 2 or more dimensions and a different one to 2 or more dimensions, then you glue them together into a 4-dimensional representation. If you need a 2-dimensional representation, you could even run another dimension reduction technique on this joint 4-dimensional space. One thing that this requires is that our 2 separate embeddings end up on comparable scales. That's doable, and sometimes this makes sense as a process to do, but it can be problematic. One of UMAP's key strengths is handling a notion of local distance, so one might naturally ask if we can use those mechanics to help fold together 2 embeddings. And the answer would be yes. This looks quite natural when you actually look at the internals of UMAP. We've already made decisions around, I looked at the chat window, sorry. Yes, I will send out the slides. Right. We've already made decisions around how to fold together different notions of similarity in our UMAP embed graph. We fold them together 2 edges that correspond to each point's notion of their distance to their various nearest neighbors. And remember, that was non-symmetric. So we folded those together to generate a symmetric edge. Those notions of gluing together fuzzy topological representations generalize fairly nicely to composing any of our underlying weighted UMAP graphs. As long as we stored our models, we can access those underlying graphs and fold those graphs together to create a new single UMAP graph, which, when we embed that into low-dimensional spaces, gives us a representation of joint representation of both feature spaces. This is a pretty natural extension of the theory that UMAP is built on top of, and as smooth extensions like this are some of the reasons that we're pretty happy with the underlying mathematical framework that we've built UMAP on top. The 3 notions, the 3 very natural notions of combining fuzzy sets correspond to intersection, union, and a sort of a contrast, which is very experimental, as opposed to the rest of this, which is fairly experimental. I typically go with the intersection operator, but this is all still pretty new, so your mileage may vary. There we go. Here's a quick example of how I might go about doing that. I took 2 embeddings of beer styles based on very different representations of that data. The embedding on the right represents beer styles by their median reviewer rating on a variety of quality axes, like aroma, appearance, palate, taste. I look at the L1 distance between the styles, and I embed them into a 2-dimensional Euclidean space with UMAP. The embedding on the left is derived from categorical features, which are hard to combine with continuous ones like scores. This particular one expands out to 33,000 dimensions, which if I just folded it together with my 4 continuous dimensions would swamp my analysis. In this model, I decided that 2 beer styles were going to be similar if they were viewed by the same set of reviewers. I represent each style by a bag of reviewers. I induce a Jacquard distance between the sets. Bob's your uncle. An equally interesting task might have been to treat the reviews as documents, and I could have done a document embedding on the reviews corresponding with each beer style. And then I could have folded that into my analysis. In both cases, we colored up points by median overall rating. You can see from the plot on the left, I'm telling you a little minor story from here, what's sort of going on. Happoshu and Japanese rice lagers. Happoshu is a Japanese low malt beer, and Japanese rice lagers, which are remarkably similar, are often reviewed by very different people. That's the plot on the left. On the other hand, if you look at the plot on the right, you see that they have very similar aroma, appearance, palate, and taste. We might want to fold these together to get a more consistent space for determining what style of beer you might want to explore next, given your particular tastes. Folding these models together is remarkably simple. We've overloaded the arithmetic operations directly on the models that we've constructed. We fold them together, and you see very quickly that this pulls together, uses the space on the right to pull together Japanese rice lager and Happoshu. And so now you know that if you enjoy one of them, it might be worth enjoying the other one. We've maintained the overall more complex and interesting structure of the reviewer embedding, but we've tightened it up with extra information derived from the embedding on the right. All right, we spent a lot of time looking at 2-dimensional embeddings, partially because visualization is a great way to explore data, and partially because pretty pictures make good slides. What if you don't care about visualization? Maybe you're worried about distorting the intrinsic manifold we're talking about. If your data lived on a 3D sphere in some 10-dimensional ambient space, then forcing it into 2 dimensions will definitely distort the structure of your data. If you don't need to visualize your data, then there's no need to embed it into 2 dimensions, or even embed it into a Euclidean space, but that's beyond the scope of this talk. We could talk about that later if you're keen. This generally comes up when you want to use Umap as a pre-processing step for a downstream task. Here, we just adjust our end components from 2, the default, up to 8, or whatever you'd like. And we've embedded those 60,000 fashion MNIST points into an 8-dimensional space, a summary of which you can see on this slide. This is less likely to suffer from that crowding effect that you might have when sort of crushing things down into 2 dimensions. Now, let's say our downstream task of interest was clustering this fashion MNIST data, independent from the labels. We're going to start off by running k-means on our original 784-dimensional fashion MNIST data. We'll then find out how well we did. One way to evaluate cluster results in the presence of labels is to use the adjusted RAND score to measure the cluster similarity. This is a measure of how well clusters match their labels. 0 is terrible, 1 is perfect. We get a 0.34, 0.35. That's pretty reasonable. So since we aren't visualizing, we can use those extra lovely dimensions to help us untangle our clusters. We embed into 8 dimensions, we run k-means on this representation, and in doing so, we improve our adjusted RAND score quite considerably, up to 0.46. That said, dimension reduction won't always improve all downstream tasks. It does often help with clustering tasks due to helping to alleviate a problem that occurs with high-dimensional data called cursive dimensionality. It also can be helpful in speeding up a variety of other machine learning algorithms, just in general. All right. Up until now, we've dealt exclusively with the unsupervised learning problem. But sometimes you either have or can get your hands on a set of labels. Maybe you did that by searching the literature or by tasking a small horde of grad students to hand label your data. Maybe you didn't get many labels because it was so time consuming, but some labels are certainly better than no labels, right? In that case, we'd like to incorporate that knowledge into our model. Enter semi-supervised UMAP and fully supervised UMAP if you have enough labels. The way to think about supervised UMAP is that our supervised labels also induce a distance between your points. So points with the same label can be pulled closer to each other, and points with different labels are farther from each other. So this pulls together members of the same class while still respecting the distance measure that you've induced across your data in the first case. So it's not a fully supervised learning problem. You're folding together the supervised notion of distance with your original notion of distance that you believe is true. You can see from the examples on the left, on the far left, that's fully supervised UMAP, where we know the classes of all of our points. This is, again, the fashion MNIST data set. If you nudge over on the right, you can convey an unknown class by, instead of handing in a full vector of labels, you set some of those values to be -1. The model knows to, or the code knows to say, oh, -1 means I don't know what class you belong to. We can use this to hide a certain portion of our labels and pass that in. This reduces the amount of separation that our model can learn from the classes, but that's okay because it's cheaper to do. All right, this actually fits very nicely with our clustering problem from before. We can make use of partially labeled data along with a higher dimensional embedding and see how we do on our task. Here, the labels take the form of a masked target vector, as I was saying before. We provide half the labels at random. We set the rest of them, we mask them out to -1 to say these are unknown labels. You apply k-means as before, and not surprisingly, we see further cluster quality improvement. Providing labeled information about the classes you care about clustering is a super way to ensure that the clusters you get out match those labels. All right. Another approach for doing the same sort of thing would be to use parametric UMAP to learn a classifier and a UMAP embedding simultaneously via a shared network. This can allow you to leverage a small number of labels to build an effective classifier. The better UMAP is at splitting classes in an unsupervised manner, though, the more effective this will be. Here you see, for example, MNIST is achieving, on the far left here, very high classification accuracy, even on this far left, despite only having 4 labeled items per class, and that's out of a data set size of sort of 70,000. That's very, very few labels. In contrast, a data set like CFAR, which UMAP fails to do very much with, shows no boost in performance at all. Many data sets fall somewhere in between, so there's a lot of scope for significant classifier boosting in low label regimes. All right, I spent a fair amount of time working with embedding categorical data using UMAP in many of my other lives. This kind of data tends to highlight a few really interesting problems with our initial version of the UMAP algorithm, and I wanted to share some. So these are the problems with categorical data. If you want more details what I mean when I say embed categorical data, I'll refer you to a talk I gave at PyData LA in 2019, and then you can come back to this one. But suffice it to say, the problem really comes down to the fact that in categorical data, you get tied distances, and often lots of them. The worst of those tied distances are points that are maximally similar or maximally dissimilar. Maximally similar is that problem of duplicate points. And the problem, the maximally dissimilar, is the problem of points that have nothing in common with any of the rest of your data. Sort of categorical set intersection of 0 with all your other points. So this can happen in continuous data, but it's way less common than it is in categorical data. All right, here's a quick embedding of breweries from around the world, where 2 breweries are similar if their beers were reviewed by the same sets of people. In my PyData talk, I go into a lot more detail about this particular embedding, but for now, we'll just treat it as a point cloud. All right, to show you what can happen, I'll replicate one of those points 500 times. And we look at the results. Our purple points here are those duplicate points that I've added. The first thing that probably leaps out to you that those points are all identical, and yet they're scattered in a diffuse cloud. This is because each of them asked for its 15 nearest neighbors. It got 15 randomly chosen identical copies of itself and decided they were maximally similar. Remember, there were 500 ties for its nearest neighbor. How does it decide between them? You're looking at coin tosses or ordering. Every dupe did this, and they got some random selection of points back as its nearest neighbors. The layout algorithm pulls together points that shared edges and pushes apart points that did not. The result is that cloud you see before you. This is problematic in two ways. First, it's a bit unintuitive to have a single point being mapped to a variety of locations. Second, it means that none of these duplicates will draw an edge to any of their true nearest neighbors in the main point cloud. Those points are going to be the 501st to 515th nearest neighbors in this particular case. So that disconnects this cloud from the rest of your data and prevents you from learning anything about it. Any of your datapates, in fact, with more than n neighbors, or 15 in this case, duplicates, will form these isolated cliques with their duplicates and be cut off from the rest of your data. All right, easiest way to avoid this problem is to set unique equals true within UMAP. And that'll result in this particular embedding on the, where the embedding on the right is or left was the original one with no dupes. The one on the right is the dupes all being mapped down to a single point within that space. You'll notice again, stochastic nature of UMAP, those don't line up well, but you can see that the general structure is there. And if you flip them in the y-axis, you'd see they match up very nicely. All right, at the other end of the spectrum, but equally problematic, are points that are maximally dissimilar from all other points. I've added 100 of these into our data set to see what would happen. And what happens here is that each of those points asks for its 15 nearest neighbors. Now, it has nothing to do in common with any points in our data set, not even the other isolates that I've added. So it's got a maximal Jacquard distance of 1 to everything. Thus, it's handed 15 random equidistant points, i.e. it is tied for nearest neighbors with all points within the data set. It decides that all of those are maximally similar, and it tries to pull those randomly selected 15 points towards it. Here, a set of our legitimate points were weakly anchored to our main manifold, and so when we symmetrized the UMAP graph, they got pulled over by these very confident points that they were their best friends. And those legitimate points, these red points over here, got pulled off into this spurious cluster and separated from the rest of our data. Another good way to see this, what's happening under the hood here, is to plot the UMAP connectivity graph directly. This is umap.plot connectivity. You pass it your model, and that's going to reveal that UMAP graph that we've been talking about. And it also reveals very quickly that that densely connected cluster on the right is in fact uniformly randomly connected to the rest of our manifold, which should make you suspicious. In case you're curious as to how to get that structure directly, because you like playing with graphs more than you like playing with embeddings, you can access that via the .graph underscore property, which is just a SciPy sparse CSR matrix. All right. Trimming these maximally distant edges is now the default behavior for any bounded distance measure like Jacquard, and its categorical friends, but it's something to be aware of. So this will happen quietly under the hood if you end up using Jacquard. You could turn it off in your data by setting this value greater than your metric's maximal distance. So if you say disconnection distance of 2, it won't do anything for your Jacquard metric. But if you've got a non-bounded metric like L1 distance, and you don't want to allow any edges between points that are further than a certain distance apart, you could set this directly via the disconnection distance parameter. It defaults to infinity for non-bounded metrics, but it's easy to set it lower if you know something about your space. All right. Under the hood, what we're really doing is cutting all of the edges greater than that distance from the UMAP graph before we're doing an embedding. As a result, these points don't have a meaningful notion of distance in their space. Their coordinates are set to NA and suppressed by our plot by default. You should be aware of that particular behavior in case you have a downstream task that consumes your UMAP results. If your downstream algorithm, say a clustering algorithm like k-means, doesn't handle NAs, you may be forced to filter those rows out yourself before moving on. A recent pull request to HDBScan that I modification I made to HDBScan allows it to consume those NAs and drop them into the -1 or background cluster. All right, this wraps up most of our whirlwind tour of UMAP. Have a look at the doc page for more details. Feel free to check out our GitHub repo where all this code lives. Feature requests, bug reports, and most importantly, pull requests and code contributions are always welcome. Even if you're just keen to help improve the documentation or show off your most recent use cases, we'd be very happy to have you contribute. You can install the code via pip or Conda Forge and try it yourself on your own data. And so, but one thing Marlon movies have taught me is that after the credits, there should always be a short teaser. And so if you've already downloaded it and tried it on your data and it's still taking too long, I've got a two-step process for you. Step one, buy a GPU. Step two, look at rapids in QML. Corey Nolet and his friends over at NVIDIA have done a great job developing a number of excellent machine learning algorithms on GPU, including UMAP and HDBScan for that matter. And they run very quickly and are quite solid and are a really nice way to scale up your performance if you're interested in running a UMAP on more data than we can normally handle. All right, so I think that more than wraps up my 35 minutes of talk, especially with technical delays. But I'm happy to stick around on the call and chat with people for as long as they would like. Maybe the internet connection is stable and we'll be able to even hear each other. That'll be fantastic.
All right, so thank you so much, John. And should we start with the question and answer now? Are you ready?
Sounds reasonable. Yeah, should I try to turn my screen on again, or what do we think?
I think you can share and turn on your camera now. So I start reading the.
Okay, I will see if I can.
I start reading the questions for you.
Sounds great.
Okay, so the first question is for the GPU. Does UMAP have any memory problems when running on the high number of data points when you work with the GPU? Because GPUs usually memories is a bottleneck.
So this is, I mean, it's designed to be run on a large memory GPU. So not the GPU that you normally have in your computer, those 24 gig of RAM GPUs that you can buy directly from NVIDIA and use for machine learning training. At which point your main limitation is not compute time, it's fitting it in memory on the GPU. So yes, but it still lets you scale significantly farther than you could run on your laptop or even a large memory CPU box.
Good. Thanks, John. So the second question I received here is, in single cell, people actually two commonly use algorithm for visualizing high dimensional data point. One is t-SNE, and the other is before by Lawrence de Martin. And for the last 3 years, I see the trend of using UMAP. Can you have a rough comparison between these two methods?
Sure. I will give you the quick answer off the top of my head. And for more detailed comparisons, there are a number of articles online you can poke at, and we do a fairly detailed comparison in the paper that I referenced, the original UMAP paper. The biggest difference I find there are two big differences, practically speaking. Speed, UMAP tends to be faster. If you want to embed into a higher dimension, UMAP allows that. That's quite expensive to do with t-SNE. It's highly optimized for embedding into 2 or 3 dimensional space. The other is the global relationship amongst the data points. So I would call them the moderate relationships amongst your data points. Your clusters, when you do a UMAP embedding, tend to be laid down nicely and related to each other according to a more global structure within your data set. This has got 2 reasons. One of them is just that we initialize with a spectral embedding, which you could do with a t-SNE, but it isn't particularly common, which gives you some initial global structure layout. The other is the cross-entry function that's buried under the hood in UMAP, which has been shown to do a decent job of recovering more of the global structure than the optimization function within t-SNE. And so a little better global structure, a little less blobby, a little faster would be my short answers. That said, t-SNE is a great algorithm.
Yeah, but theoretically we
cannot sort of the father of all of this.
But theoretically we do not have any guarantee for the global optimization for this method.
Absolutely not. And I mean, theoretically, there are no you've got no guarantees in either of these. Both of these styles, most of the manifold learning styles of algorithms that are like very successful are quite hard to analyze.
Right.
And partially is that's, yeah, let's go with that.
Thanks, John. So the next question from Auda Addison. This may not be related to dimensional reduction, but is the density-based clustering being replaced by graph-based methods such as Louvain clustering?
In my analysis, yes. In global, no. Louvain is a great algorithm. I have a colleague named, in fact, if you like graph analysis, I have a colleague named François Théberge and Valérie Poulain, who have done an ensemble clustering of graphs algorithm, which does a voting bag of Louvain clustering style methods that does very, very well on graph clustering. So I would preface that with, that is the right thing to do when you have natural graph relational data. I am not sure that that's the right way to go. I don't think you want to use a Louvain or a graph-based algorithm when you're dealing with a graph that has been induced from a nearest neighbor structure on a metric space. So if you're coming from a metric space, the nearest neighbor structure is being used to represent the manifold, and traditional graph algorithms won't deal with that cleanly or well. They can run on it, certainly, because it's a graph, but I don't think it's the right thing to do. I think you want to treat sort of density-based vector space algorithms when you're dealing with a metric space, and you want to live in graph land when you're dealing with proper relational data.
Right.
But if you're in graph land, Louvain and Ensemble Louvain are totally the right things to do. I love them.
So the next question is from Austin Chu. The question is that, when you project new data into a UMap embedding, is the projection basically re-performing UMap with the new data points appended in the original data set, or it can be apply some transformation to the new data point directly?
Yeah, so the really nice thing with the parametric UMap, it's not just reapplying UMap. It learned a functional transformation, so a mapping, from the original space down into the UMap space. The objective function under the hood on the neural net was the same as our UMap objective function, but we're not doing any learning updates by doing the transform. So it really is just dropping a function through a mapping into a low-dimensional space. And I think this is the key insight that I think you're hitting on here, is that out of distribution problem that can crop up here. That is, if that point looks nothing like any of our previous data, we're not learning its relationship with respect to all of the other points as we would be doing an aligned UMap. We're just guessing as to where it would go in our low-dimensional space. And so it will perform poorly for out of distribution data. So it's just that projection, which makes it very fast though. A game you could play if you wanted to sort of is to train on that new point. You can sort of do online learning games where you take your initial network and you hand it some new data, and then you update the weights to try to learn new structure contained within the data. And so that would be my suggestion for that. You do transform to embed into the new space, and then you do an offline process on the side where you're updating your model to take into account new data and make sure that you don't get any data drift occurring. Does that make sense?
That makes sense, John. And related to these questions, so there are, in the field, especially in biology, people have some challenging problem. They call it Bash effect removal. When data, maybe the same data or the two data sharing some basic structure there, they perform in two different labs. Can align UMap helps in this case?
Ooh, that's interesting. You have labels that anchor the two sets of data together,
may have
but they don't
label that
fully
anchors the two, right? Right. But essentially, there are some part of the data we don't know, but some we know that they share some structure. They share some cell types.
Yeah, and so if the two labs have performed experiments on the same some subset of overlapping data.
That's right.
And perhaps have some extra data that is not included in the other. Aligned UMAP is exactly the right thing to try in that case.
Okay,
I'd be really excited to see that as a use case written up.
That is wonderful, because the field is actually, this is a very tough problem in the field right now.
Very cool.
The next question from Alda Addison is, is there a quantitative way to measure how similar are two visualizations?
So the short answer is there are lots of quantitative ways to measure how similar visualizations are to each other. I'm going to refer back to the beginning of my talk. It depends on what you mean by distance. And so the most trivial way I can think of to measure how similar visualizations are to each other is there are two images, and we can do image embedding. We can do convolutional nets on images. We can do all of these things. If you had labels, and you often have labels when you're embedding the same set of points into two spaces, you could say, I can align them, rotate them, do a Procrustes transformation to match them up, and then I could measure the sum of the point-wise differences between me and my matched point from the other set. Another game you could play if you were really interested, it depends, this is what thing you're interested in. I've seen people play this with graph embeddings. Again, Francois Teberge has done this with graph embeddings. You look at the cluster structure and you say two visualizations are similar if they result in the same cluster structure. So I perform clustering via some algorithm, HDB scan, k-means, take your pick, and I do another embedding with a different visualization technique and do another clustering. Now that results in two clusterings. I can look at the adjusted RAND index between those clusterings and say, hey, these two embeddings result in very similar clusterings. Now, all three kinds of measures will result in vastly different distance measures across your visualizers. They're all right. Some of them are useful. Some of them might be appropriate for your task. That would be up to you at the end user.
Right. The next question, some people in single cell, some people use PCA before UMAP. Do you recommend that, or you think that UMAP can be applied directly from the raw data?
Yeah, so we used to recommend that in the original versions of UMAP, which I think is why that sort of exists. It's often done as a pre-processing step for many expensive things. I used to do it before I ran TS&E because I had a hard time getting TS&E to scale to high dimensional data.
The next question.
UMAP is now based off of a library. Okay. UMAP is now based off a library called PyNN Descent that Leland McInnes has more recently developed directly in high dimensional space. And so doesn't require the PCA as a pre-processing step anymore.
Okay, so what is the minimum number of data points?
So the minimum, the short answer is I'm not sure. You can get meaningful results on very small amounts of data. They tend to be less and less stable as you get smaller and smaller amounts of data. And that's typically because the degrees of freedom on the manifold structures can get quite large. And so you get a lot of instability in very small amounts of data, but you still get easy to explore visualizations. And so I've run UMAP on hundreds of points with good, strong structure under them and pulled off interesting.
Right. So some of the last questions here, because we almost went out of time. The question from Stephen Brooks. Like a month ago, there is a reprint from bioRxiv from Leo Basta. They said that extensive destruction incurred on the global and local properties of biological patterns relative to high-dimensional ambient space. Are you aware of this? And also, there was a discussion further that he said that people should stop using t-SNE or UMAP. What is your opinion on this?
So I had a quick glance at that paper because someone threw it. I think you threw it my way, Son. Is that the paper in question? Do you think?
Yes, that is the paper.
Perfect. I think James Melville had a great response to this when we were chatting about it, and I think his fundamental issue with that particular paper, the thing I disagree with the most, is the goodness measure that they're measuring in that paper is a good representative of global or local structure within the data. They look at correlation amongst sort of distance pairs. I would go back and revisit that if I were you. It's very non-intuitive things for embedding things that I think are quite useful. The extra criticism that I noticed that came up a lot there was people are doing UMAP and the results are spurious. They're making claims with just a UMAP plot. And I don't know if that's true of the literature. You all would probably know that better than I. Again, I would say that UMAP is and any visualization technique is useful for providing intuitions and developing hypotheses, which you then go and validate and test with experiments after the fact. And so I don't think that is a particularly valid criticism either, other than, don't do bad science. I agree, don't do bad science is a useful statement. The last thing I would say is that I have seen quite a lot of practical, useful cases where people are using UMAP and validating the results in a wide variety of fields, and those results are being validated. And so it has suffered succeeded the test of time and the test of providing useful value to a lot of productive, useful, validated scientific tasks. And so I don't think that the criticism that it's purely spurious pictures or whatever is particularly valid.
All right. Thank you so much, John. The last question is from me. In order to avoid the criticisms on not being able to solve the global optimization for NP complete problems, are you aiming to solve P equal to NP?
I think I'll pass on that one, at least in the short term.
All right. All right. Thank you so much. I think UMAP is especially helpful algorithms especially for single cell data visualizations, and we use it a lot here. All right. Thank you, John, so much for giving a great talk, and thank you everyone for spending time asking a lot of questions. We have a lot of immense questions here that are not answered. We will send this to John and we'll follow up.
Happy to respond in an email to all of those questions.
All right. All right.
Son, what is the easiest way for me to get my slides to participants? There's a bunch of links. If I send you my slides, do you want to link them off of the webinar talk page?
Definitely, definitely.
Perfect.
All right. Thank you so much, John, and everyone.
Absolute pleasure. Enjoy.
Bye. Thank you, John. Thanks, everyone.
Bye-bye.